50 million years from tonight, the room you are sitting in will be gone. Not abandoned, gone. The city around you will be gone too. The roads, the bridges, the buildings, the ground beneath them may be buried under an ocean, crushed between continents, or pulled deep into the earth. Then, one day, a scientist drills into the rock and pulls up a long cylinder of stone. Most of it looks ordinary, grey, brown, layer after layer of nothing unusual, until they reach one thin line. Something happened when that line formed. The planet warmed, the oceans changed, strange materials appeared, spread around the world, and then suddenly stopped. The scientist will never see our buildings, and may never realize that billions of people once lived here. But that thin line will be us. So what happens when we find a line like that from the distant past? Do we call it a period of natural warming? A burst of volcanic activity? Do we notice anything unusual at all? And how would we tell the difference between a natural disaster and the remains of an industrial civilization? In 2018, 2 NASA scientists decided to treat that question seriously. They did not claim that someone was here before us. They asked whether we could ever know. Because Earth is very good at hiding what happened on its surface. Given enough time, almost everything disappears. Almost. And that last word is where this story begins. Before we settle in, if you enjoy exploring questions like this with me, subscribing helps others find their way here too. And I would genuinely like to hear your thoughts below. I read every single comment. Now, let's begin. The name can send you in the wrong direction before you read a word of the paper. The Silurian Hypothesis. It sounds as if someone found something, maybe an old structure, or proof that a door into Earth's past had finally opened. That is often what people expect when they first hear it. A discovery hidden behind careful scientific language. But Gavin Schmidt and Adam Frank were doing something much more limited when they wrote the paper in 2018. They did not claim to have evidence of an ancient civilization. They asked whether we would be able to find that evidence if such a civilization had ever existed. The paper depends on that difference. Their question was simple to ask and hard to answer. Suppose an industrial civilization rose and fell on Earth tens of millions of years ago. What would still be in the rock today? Buildings, tools, and roads would probably be gone. Over deep time, rock is ground down, dissolved, buried, and recycled. So Schmidt and Frank turned to chemistry. They asked whether industry working across a planet could change sediment in a way that geologists might still detect. Heat belongs in the question too, because a global industrial system can change more than the material buried beside it. You can think of it as a blood test taken long after the body itself has disappeared. You are not trying to find the person. You are checking whether any sign of that person remains. The body is gone, and the room has been rebuilt many times. But if something changed the body's chemistry for long enough, a trace may survive in the right sample. It may be small and difficult to erase completely, but still measurable. Astrobiologists already use this kind of reasoning when they search for life on other planets. They do not expect a building to come into view. They study gases in an atmosphere that seem out of place, or isotope ratios in rock that may have a biological cause rather than a geological one. The activity is inferred from the changes it made to the planet. Schmidt and Frank applied the same logic here on Earth. Could geology preserve signs of a civilization in much the same way that it preserves signs of ancient seas? The limit of the paper needs to stay clear. It never says that a pre-human civilization existed, and it never points toward one. Schmidt and Frank kept the question open on purpose. They built a way to test the geological record against one possibility without choosing the answer first. If Schmidt and Frank chose the answer first, the geological test would tell them nothing. So if you open the paper expecting a discovery, you find a method instead. That method leads to the next problem. If ruins are unlikely to survive, what traces could industry leave on a scale large enough for the planet to keep? Think about what happens when a toxin or a long chemical disturbance stresses a body from within. The surface may look unchanged at first. Inside, ratios begin to shift. Compounds appear in the blood that were not there before. The cause can disappear while the chemical record remains. A planet has a record like that too. That record runs through the planet's cycles. Carbon moves between air and rock, and isotope ratios change depending on what burns. Meanwhile, sediment gathers year after year on the floors of ancient seas. Some of the chemistry from the surface settles with it. Push those systems hard enough across the whole planet, and the sediment changes with them. Those were the traces Schmidt and Frank considered in 2018. They were not searching for a buried structure, or an object that could stay recognizable after 60 million years of geological pressure. They asked whether a technological civilization could leave a chemical fingerprint in sediment. That could include carbon isotope shifts from large-scale combustion, synthetic organic residues, unusual accumulations of certain elements, and changes across several planetary systems at the same time. 2 years earlier, in 2016, Colin Waters and a team of researchers had approached a related question from the present. What would the Anthropocene look like in the rock record? Forget the human world as it looks around you now. Imagine only the thin sediment layer a geologist might examine in 50 million years. Waters and his team described no visible structure. They described chemical and isotopic disturbances appearing together in different environments during the same narrow period. This corrects an easy assumption. You may expect industry on a planetary scale to leave one enormous signal that nothing else could explain, one object that settles the matter by itself. Geology is rarely that generous. Natural processes can shift isotopes, and carbon can accumulate during volcanic episodes. One unusual result may still have several possible causes. Several independent signals arriving together are harder to dismiss. Each is measured in a different way, but they point toward the same event. Then every natural explanation has more work to do. One trace may be ambiguous. A pattern gives you more to test. Their agreement carries the weight, even when each line is modest on its own. The farther back you search, the stricter the proof has to become. It cannot become easier simply because the event would be rare and the record is incomplete. Researchers would need a bundle of markers from different places where sediment formed. They would need different chemical proxies to meet in the same narrow period. The result would have to be unusual enough to make a working geologist stop and check it again. Each proxy has to survive its own natural comparison. The bar is high because it has to be. That gives researchers a clear target. You cannot hold it in your hands like a tool, and it will not look like the wall of a missing city. It is closer to a disturbed bloodstream. A planet's chemistry changes across several systems. Then some part of that change settles into sediment and isotope ratios at the bottom of ancient seas. Geology may lose the object itself while keeping a record of what the object did around it. So why did ruins seem like the obvious place to look in the first place? Think about what is outside your window. If it is dark, imagine the same view in daylight. There may be roads, buildings, a water tower, perhaps a bridge. They feel permanent because you have known them for years and they have barely moved. It is easy to assume that something built to last will stay there. That sense of permanence comes from the short timescale of a human life. A road may last through several lives and still be temporary to the earth. It is like checking a sandcastle an hour after you built it and deciding the tide will never reach it. Geology keeps a very different clock. Gavin Schmidt and Adam Frank worked through this problem in 2018. They wanted to know what the geological record would do to the materials left by an industrial civilization. Their answer was blunt. Anything exposed at the surface begins to break down almost at once in geological terms. Rain and wind start wearing at it, while roots open the first cracks. A steel bridge left on its own will not remain recognizable to a geologist for 10,000 years. Corrosion and biological growth take care of that. Roads split apart, foundations sink, plants work their way through concrete, slowly enough that you may not notice from one day to the next. On a geological clock, the change does not stop. Plants can keep widening the same cracks for ages, long after the first damage was too small to notice. Burial changes the material again. Sediment covering an old surface does not preserve everything beneath it like a photograph. It presses down. Chemical reactions alter what was buried. If the material goes deep enough, heat changes it too. Across tens of millions of years, tectonic plates fold and move the sediment. Some former surfaces are carried down until their original materials no longer exist in a recognizable form. Deep time usually breaks a landscape down instead of storing it intact. Cities feel impossible to miss because we live inside them. We know how to notice a skyline, a bridge, or the straight line of a road. A rock does not remember a city in the same visual way. What looks enormous to you tonight may become a faint change in a layer of sediment. The skyline is visually loud because you are standing near it. The rock has no reason to keep that outline. Some details do survive. Rapid burial under volcanic ash can preserve them. So can a stable chemical environment or the right sediment in the right basin. Those conditions are possible, but they are unusual. For every Pompeii, there are 10,000 sites where recognizable objects turned into chemistry long before anyone could look for them. So Schmidt and Frank did not begin by expecting objects to survive. A more ordinary result would be an occasional chemical disturbance in the rock. Perhaps certain isotope levels rise, the carbon record shifts, a thin layer shows that material gathered and later burned. If a civilization leaves a signal that lasts, it may look like a fingerprint in sediment rather than a ruin. That makes towers, bridges, and roads some of the first evidence we should expect to lose. Then what can last longer than the objects? Imagine a factory beside a river. It operates for a century and then burns down. The walls fall, machines corrode, a few generations pass, and the site becomes a field. Later, the field becomes a suburb. Almost nothing at the old factory can still be found. Downstream, the riverbed has kept a different record. Mud caught the heavy metals, particles, and trace chemicals released by the factory. New sediment covered them, layer by layer. The factory disappeared, but some of what it released stayed in the mud. What lasts is the mark the factory left on its surroundings while it operated, including altered chemistry downstream. This is easy to miss when you imagine evidence from the distant past. You may expect hardware, walls, or some familiar shape that can be pointed out. Yet the surroundings may keep a record longer than the object itself. They keep the changed chemistry left behind while the object was working. In 2016, a research team led by Colin Waters studied what modern industry has already put into the geological record. They examined sediment forming today, rather than waiting for some future era. They did not find a layer of buildings. They found many kinds of disturbance in the chemistry and makeup of sediment and rock. The list included carbon, nutrients, particles from combustion, trace metals, synthetic materials that did not exist before the 20th century, and radionuclides from nuclear testing. These signals are entering rock layers quickly and across enough of the planet to be detected globally. Monuments are not what make the signal visible. Changes to the planet's chemistry do. Chemical evidence creates its own problem. A disturbed layer does not automatically point to industry, because nature leaves disturbed layers too. A volcanic eruption deposits ash and altered metals. A mass extinction changes the chemistry of ocean sediment. An asteroid impact puts iridium into the rock. Geologists already know many disrupted layers with natural explanations. If you find a strange layer, you have found a reason to investigate carefully. You have not found proof that someone built something. What you need is a pattern of chemical change that does not fit the known natural causes from that period. It would have to build up in a way that looks more like industry than weather. The way the signals arrive together may tell you more than any surviving object. Its timing and chemical context need to make the known natural causes harder to use. At that point, reading rock begins to resemble reading a blood test. A doctor can look for markers of activity even after the body has changed. A geologist would look for a ratio outside the natural range, or an element at a concentration that rock alone cannot explain. The chemistry would have to contain something that the known conditions of that era had no reason to produce. River mud may last millions of years longer than the factory walls. We usually think the walls are the record. The mud may be the part that keeps it. If cities vanish that easily, does the ocean keep a better memory? The seafloor seems like it should remember. We tend to imagine it as dark and still, a place where things sink, become buried and stay there. Sediment falls slowly through the water. Layer after layer gathers over millions of years. Cold and pressure seal away whatever reaches the bottom. It sounds like the place where Earth would keep its oldest records. Some of those records do survive. Marine sediment preserves chemistry, microscopic shells, and traces of what happened in the water above. Scientists have learned a great deal from deep ocean sediment, but the ground beneath that sediment is doing something you cannot see. It moves far too slowly for anyone to notice during a human life. The seafloor itself is moving. New oceanic crust forms today along mid-ocean ridges. Tectonic plates pull apart there, allowing molten rock to rise and harden into fresh seafloor. That crust then spreads away from the ridge by a few centimeters each year. Far across the ocean basin, where it meets a continental plate, the crust dives back into the mantle and melts. New floor forms at one end, while old floor disappears at the other. This has continued for billions of years. The archive has a moving foundation rather than a shelf fixed beneath the ocean. Imagine a whiteboard that is erased and reused throughout the day. You can cover it with writing in the morning. By the afternoon, someone has wiped that surface clean and written over it. The old words are not hidden beneath the new ones. They are gone. By afternoon, the board can hold an entirely different record. Schmidt and Frank followed this cycle in 2018 by looking at how oceanic crust ages as it travels away from the spreading ridges. Almost none of it survives beyond about 200 million years. That sounds like an enormous stretch of time, until you compare it with Earth's age of 4.5 billion years. The seafloor does not hold a record of most of the planet's history. It keeps a much more recent one and replaces it continually. Nearly every older seafloor surface has already been carried away through the same cycle. Even the oldest known pieces of oceanic crust are only a few 100 million years old at most. That is ancient beside any living thing, but it covers a small part of Earth's story. Most of the Pacific floor is younger than 180 million years. In geological terms, the floor beneath that ocean is fairly new. The ocean can still keep useful evidence. Sediment can ride on moving crust for tens of millions of years, carrying chemical signals until the floor beneath it disappears. That is a very long memory by human standards, while still being a short one beside the oldest parts of Earth's history. The ocean does not work as a safe vault that remains untouched through the deepest stretches of time. Its floor erases itself too quickly for that. So the backup archive, many people imagine, has a limit. If the seafloor is temporary, where should we look for a longer record? The useful places are more selective. Some lie along continental margins, where rivers carry sediment to the edges of land, and it can build up instead of washing away. Others are enclosed basins, such as bays or inland seas, that are almost cut off from the wider ocean. Water moves slowly there, giving debris time to settle. There are also unusual sediment traps, where local conditions favor burial and preservation. These are corners where material can settle faster than local erosion or disruption removes it. Think of the geological record as a few pages that happened to survive a fire. Nobody selected those pages because they contained the most important parts. They survived because they were shielded in a corner. Geology works in much the same way. What remains is what happened to be protected, not a complete account of everything that happened. This is where an easy mistake can take hold. You may decide that if the ocean cannot keep a perfect record, the search has already failed. But geological preservation has always been uneven. The record is a selection, not a complete count. We do not need every part of the ocean to remember. We need the right places to preserve enough of the right material. Continental margins can sometimes do that. Sediment may gather there for hundreds of millions of years without subduction carrying it back down. The Cariaco Basin off Venezuela holds layered sediment reaching back 12,000 years. Some layers are fine enough for researchers to follow climate changes almost season by season. Enclosed basins can preserve material even better. Deep water in the Black Sea is nearly stagnant. That discourages the microbes that would otherwise consume organic material before it could fossilize. The unusual conditions inside a basin may help it keep exactly the kind of evidence that is lost elsewhere. What makes these basins unusual can also make them useful preservers. Even a good basin preserves only part of a wider signal. A chemical pulse that spread through the whole ocean might appear clearly in one basin and leave nothing in the next. One sediment core contains evidence while a nearby core is silent. Two cores drilled only a few kilometers apart in the same basin can still give different records. A missing trace in one core may reflect local preservation rather than the absence of the original pulse. The evidence is partial. Reading it well means knowing how much the core can tell you and where its limits begin. We do not have a complete map of these deposits. A drill core may reveal a basin that researchers expected to be silent. Another basin may look promising until the core shows disturbed layers, oxidation, or sediment mixed too thoroughly to read. The inventory is incomplete, and it will remain that way. Once you accept that geological memory is selective and depends on local conditions, the search changes. A single archive cannot carry the whole answer. The next task is to find markers that can survive selective burial and still be recognized in a broken record. Location affects what survives, but the material laid down there carries the evidence. If oceans forget so much, what does modern industry change across the planet? Your body changes the room around it. You warm the air, you breathe into it. At the same time, the chemistry inside your body changes according to what you take in, what you burn, and what you release. An industrial civilization does something similar on a planetary scale. It behaves less like a statue and more like a metabolism. The room carries evidence of the body even after the body walks away. That metabolism moves through the atmosphere and the ocean. It also reaches the particles that settle slowly onto the seafloor. Several circulating systems change together. In 2016, a research team led by Colin Waters surveyed what modern industry had changed across the planet. Carbon was one part of the result. Agriculture had also washed nitrogen and phosphorus into waterways. Black carbon and other particles from combustion were drifting into ocean basins. Nuclear testing had spread radionuclides. Researchers could find altered chemistry in lake sediment, ocean cores, and ice. This was much larger than the mark from one chimney or one machine. Air, water, and settling particles all carried some part of the change. You may still imagine industrial evidence as something local: a smokestack, a spill beside a factory, a scar cut into the ground. But the carbon does not stay beside the place where it was released. Some enters the ocean and changes the water. Nitrogen runs into rivers and estuaries, where downstream sediment records it. Combustion particles drift away and gather in layers. Ecosystems respond as well, changing the living part of the record. Industry moves through all of these systems at once. The result does not look identical in every sample. A lake may hold altered sediment chemistry. An ocean core may catch combustion particles that settled through the water. Ice can keep radionuclides. Different materials take different routes into the record, then arrive within the same industrial interval. Timing helps geologists recognize the result. Waters and his colleagues described an acceleration of industrial processes around the middle of the 20th century. On a human calendar, the change took decades. On a geological timescale, decades are close to instantaneous. A slow change can blend into the surrounding record. A sudden one leaves a sharper edge. That narrow timing lets a geologist separate the pulse from the slower layers on either side. Speed alone cannot identify industry. Nature has moved carbon quickly before, during volcanic episodes and the great extinctions. Some events in the distant past changed atmospheric chemistry within thousands of years and left clear lines in rock. The current change has a different combination. Carbon arrives with nitrogen, phosphorus, combustion particles, and several other signals inside the same thin interval. The combination forces each natural analog to explain the same timing. Carbon belongs in that layer, but it is only one part of it. Manufactured materials may enter the same record. Plastic is the example discussed most often. In 2016, Jan Zalasiewicz and a team of researchers explained why plastics could work as a geological marker. Plastics are new to geology. They did not exist before the middle of the 20th century. No organism makes them, and no natural process creates them from scratch. They enter the rock record at a particular time, with no older natural examples beneath them. A marker that begins at one boundary and has no older examples gives geologists a line to compare across sites. The tempting image is a future excavation uncovering a recognizable bottle or food container. You could pick it up and know at once that somebody made it. That would be the strongest kind of evidence, an intact artificial object sitting inside rock. Sediment usually receives something much less complete. Plastic breaks into fragments and microplastics smaller than grains of sand. Polymer fibers become too fine to see without magnification. They are already present on the ocean floor and in river sediment. Millions of years of heat and pressure would change them further as the sediment became rock. A bottle is unlikely to remain a bottle. What may survive is a chemical signature inside an otherwise ordinary band of sediment. Heat and pressure alter the material itself as well as its shape. Colin Waters and his colleagues expanded that list in 2016. They included fragments of concrete and spheres of fly ash. Fly ash spheres are tiny hollow beads made when coal burns at high temperature. They are small enough to travel long distances before settling. The researchers also included unusual elemental ratios absent from pre-industrial rock layers. Geologists can compare the hollow shape and elemental ratios with material in older layers. These materials can appear together even if none survives in perfect condition. Their combination may be unusual because natural processes would not have assembled it on their own. Think of a stain on a wall. A sculpture in the room either remains intact or it does not. A stain can fade and still leave the wall changed. Future geologists would be more likely to find that kind of change. They would not uncover a museum of modern objects. They would find a band of rock with a different chemical makeup. That is enough to change what counts as evidence. Most manufactured objects will be broken, dissolved, altered or moved before deep burial. Residues have a better chance than recognizable relics. A geologist would need to read the composition of the rock rather than rely on its outward shape. Those residues can still provide a clear marker. Synthetic materials enter sediment as fragments and altered chemistry. Their value comes from the composition they leave behind, even when the original object can no longer be identified. A future geologist would compare that composition with the layers above and below it, looking for materials and combinations that appear only inside the industrial band. Over time, many of those signs will blur or change. Is there anything in the layer that stays tied more precisely to one moment? One group of markers looks unusually exact in recent sediment. Cores, dating from the middle of the 20th century, contain a thin line where several radioactive isotopes appear at once. Plutonium, cesium, carbon-14 above its natural level. Researchers find the line in lake beds, polar ice and ocean sediment. Waters and his colleagues mapped it in 2015 and saw the same pattern at sites with little else in common. Because it appears in unlike settings, the marker can tie separate records to the same recent interval. The source was fallout from atmospheric weapons testing. It settled across the planet at roughly the same time, leaving a date marker in the recent record. At first, that sounds almost conclusive. The material is radioactive, artificial, and globally synchronized. It seems difficult to confuse with anything else. But radioactive markers come with their own clock. Imagine writing a date with ink that fades at a steady rate. The date starts out clear. After 10,000 years it is pale, and after 100,000 years it is gone. The paper can remain after the writing disappears. The event remains historically real, while the isotope signal weakens at a predictable rate. Radioactive isotopes decay at steady, measurable rates. That decay is what allows us to detect and date them. Carbon-14 has a half-life of about 5,730 years. After each period of 5,730 years, half of the remaining amount is gone. Plutonium-239 lasts longer. Its half-life is 24,110 years, more than 4 times the half-life of carbon-14. Yet deep geological time is counted in hundreds of millions of years, not thousands. Even plutonium-239 eventually fades away on that scale. After 30 half-lives, less than 1/1000th of the original signal remains. A line that looks sharp in a core from 1963 will not stay sharp through deep time. The marker is still real and precise. Nature did not produce it on its own. Researchers can date it, locate it, and connect it to a particular decade of human activity. That makes radionuclides unusually useful in recent sediment, where enough of the original material remains to measure. Their steady decay also means the limit can be calculated rather than guessed. The line is easy to read in recent sediment, weaker in old rock, and absent from truly ancient rock. The marker is accurate within the span it can survive. Beyond that span, researchers need other evidence, such as plastics, altered carbon, industrial metals, and changed pollen. Each records a different part of the same event. Together, they can support a case that none could carry alone. Plastic, carbon, metals, and radionuclides do not survive for the same length of time. The bundle cannot depend on one of them lasting forever. Even the most artificial-looking marker in this layer will disappear before the deepest geological record is finished with it. Carbon lasts much longer and carries a large part of the industrial story. So why is carbon alone still not enough? Carbon leaves a real signal. We can measure it. When an industrial civilization burns fossil fuels on a large scale, the carbon in the atmosphere changes. Coal and oil contain very old carbon. It has been locked underground for so long that the carbon-14 inside it has already decayed away. By the time that fuel reaches a furnace, this particular form of carbon is no longer present. Burning the fuel releases ancient carbon into the air and lowers the proportion of carbon-14 in the atmosphere. The change is measurable. Chemists have followed it for decades, and it moves in the direction they predict. The atmosphere is being diluted with carbon that no longer carries the short-lived isotope. In 2016, a team led by Colin Waters identified this carbon shift as one of the clearest signs of modern human activity. It sits inside a much wider group of chemical changes that define the recent interval in the geological record. Schmidt and Frank found the same pattern while working with ocean sediment cores. The carbon change appears beside other modern signals and rises with them. It is part of the modern interval rather than a separate flicker somewhere else in the core. In a core, the carbon line should rise with neighboring markers rather than thousands of years before or after them. That makes an ancient carbon anomaly sound like an industrial fingerprint. If large-scale burning changes carbon so reliably today, perhaps the same change in an old layer would point to an earlier civilization. The carbon cannot tell us that much by itself. Imagine seeing smoke above a line of trees. You know that something is burning, and you would be right to take the smoke seriously. But the view from the forest edge cannot tell you what started the fire. Lightning may have struck a dry trunk, a house may have caught a spark, or a camper may have walked away from a flame. Several causes can leave the same smoke above the trees. A carbon spike has the same limit. It tells you that something disturbed the carbon cycle, without identifying industry as the cause. Earth has disturbed that cycle many times. Volcanic eruptions release old carbon depleted in carbon-14. Methane can escape suddenly from sediment on the seafloor. A change in ocean circulation can alter the amount of carbon buried and the amount left in the air. Large igneous provinces have also left carbon spikes from long before any civilization could have caused them. During those episodes, the crust opened and lava spread for tens of thousands of years. Each process begins differently, yet each can push the carbon record away from its earlier level. To separate those causes, geologists have to read what else changed inside the same layer. Without the surrounding evidence, a natural carbon spike might look technological. The reverse mistake is possible too. A technological signal might be read as another natural event. Both errors come from treating carbon as a source label instead of a marker of change in the cycle. So carbon is a serious clue. You would expect it to appear if an industrial civilization had changed the planet. Finding it alone, though, begins an investigation rather than finishing one. Carbon belongs in the expected evidence, but it cannot identify the cause on its own. What would need to appear beside it before the industrial interpretation became stronger? Think about an accident at an intersection. One witness can help you understand what happened. You listen, record the account, and check it against anything else the scene can tell you. Then 3 people standing on different corners describe the same sequence. They give the same direction of travel, the same moment, and the same color of the traffic light, even though they watched from separate places. Independent agreement is harder to explain away than one account, especially when the details line up in time. Sediment can provide evidence in much the same way. One unusual measurement is one witness. A carbon shift deserves attention, but a single line on a graph can still have a natural explanation. The interpretation remains uncertain until independent markers appear in the same thin interval. Other markers act as separate witnesses because geologists measure them in different ways. The size of the carbon change is less important than the company it keeps. Do heavy metals, fly ash, radionuclides, and changed pollen all appear in the same narrow band of sediment? If they do, an industrial cause becomes harder to dismiss. If they do not, even a steep carbon rise remains one account with no supporting witnesses. Each marker has to cross its own threshold inside the same slice of sediment. This is where a dramatic graph can fool you. A sharper curve or a larger number feels more certain, as though the height of the line settles the cause. Yet a vivid signal can sit in the wrong context. Carbon by itself remains ambiguous, however steep the rise may be. You can document it carefully, measure it precisely, and report every number. The measurements may all be sound while the cause remains unresolved. The height of the curve describes the size of the change, not its cause. The case grows stronger only when independent evidence agrees. The sediment must contain a coordinated group of signals in the same layer. Those signals also need to differ from whatever was already happening before that layer formed. This standard becomes important when we compare the modern record with a natural event from Earth's past. That event produced part of the same pattern without any industrial cause. It made a carbon excursion and a warming signal, then left both in sediment. The layer is unusual enough to make geologists stop when they encounter it, yet its origin belongs to the planet's own processes. That is why it is such a useful test for the carbon argument. Its value comes from comparison. A natural event can share part of the industrial pattern. The event is the Paleocene-Eocene thermal maximum. It shows how convincing a natural layer can look, and why the surrounding evidence has to be read so carefully. What happened during that event, and which parts of the modern signal still need more witnesses? 56 million years ago, something changed very quickly. Not in a week or a year. On the clock kept by rock, quickly can mean a few thousand years or as many as 20,000. Against Earth's long history, that is a brief event. Geologists call it the Paleocene-Eocene thermal maximum, usually shortened to the PETM. In sediment, it appears as a narrow band where carbon isotope ratios shift sharply. The balance of heavy carbon and light carbon drops in one direction, stays low for a time, and later recovers. When geologists reach that layer, they know the carbon cycle changed. The later recovery gives them another boundary to compare across cores. John Higgins and Daniel Schrag examined this signal in detail in 2006. They traced what it meant for the chemistry of the ocean, and the event was anything but small. Global temperatures rose by somewhere between 5 and 8 degrees Celsius, that is 9 to 14 degrees Fahrenheit. The deep ocean became warmer, and some sediment on the seafloor dissolved. Many deep-sea foraminifera went extinct. These are tiny shelled organisms that drift, sink, and become part of the sediment record. Their disappearance appears beside the warming and carbon change, rather than in a separate period. The layer appears in cores from the Atlantic, Pacific, and Arctic. It was a global event, rather than a disturbance confined to one part of the ocean. The resemblance is easy to overread. Imagine a good counterfeit bill. The paper feels right, the ink is close, and the serial number follows the proper format. Unless you know which details to check, you may accept it. The PETM has that kind of resemblance to part of the modern industrial signal. It contains a carbon excursion, warming, and biological disruption. If all you knew was that industry can produce those changes, the ancient layer might make you suspicious. All three features occupy the same narrow layer, which is why a first glance can mislead. That suspicion is understandable, but the PETM is a natural event. Carbon came from geological sources. Some may have been volcanic, and some may have come from methane released by ocean sediment as temperatures crossed a threshold. Researchers still debate the exact proportions. That debate concerns how much carbon came from each geological source. It does not turn the PETM into a candidate industrial layer. The event is natural in kind, even while part of its mechanism remains unsettled. The PETM belongs here because it shows what a natural disturbance can leave behind. Part of its record overlaps with a modern signal, and that overlap makes the test for industry harder. Why does such a close match make an industrial claim weaker rather than stronger? A piano and an organ can play the same note. If each plays middle C, a listener in the next room may have trouble telling which instrument made it. The shared note does not make the instruments identical. It only tells you that their ranges overlap. You need some feature that only one instrument can produce. The PETM produced some of the same notes. Around 56 million years ago, a massive release of carbon raised global temperatures by roughly 10 to 12 degrees Fahrenheit, or around 5 to 7 Celsius. The exact carbon source is still debated. The release happened quickly by geological standards and formed a sharp boundary in sediment around the world. Ocean chemistry changed. Some species moved while others disappeared. The carbon anomaly appears in cores from every ocean. Higgins and Schrag worked through what those changes look like when they are read from rock, and the result is clear enough to create a problem. The PETM is easy to recognize. Its signal agrees across the globe. Tools that flag something unusual in recent sediment also flag this much older natural event. A local disturbance could not explain the same carbon boundary across all of those sites. Earth can produce a rapid, severe, globally readable disturbance through its own systems. The evidence does not have to arrive slowly or look vague. The PETM left a clean line in cores from the deep Pacific, the Arctic, and the South Atlantic. Those cores turn the event into a measured comparison, not a hypothetical objection. Nature produced the disturbance, and the rock kept enough of it for geologists to follow across separate oceans. So a layer with warming, a carbon shift, and biological disruption is not enough to identify industry. The PETM had all three without cities, large-scale industrial burning, or machines. The planet was changing through natural processes. That is the boundary to keep in mind. Similar evidence can come from different causes. Each time an unusual layer seems to explain itself, the PETM gives you a reason to pause. It is a measured event in real sediment columns from the Pacific to the Arctic. It produced some of the evidence we would expect from industry, yet it had a natural origin. Those columns give researchers a baseline they can place beside any candidate layer. The PETM already establishes that something large happened. The harder question is which part of a layer could only have come from technological activity. What would a technogenic layer need that a natural hypothermal such as the PETM cannot provide? Carbon starts the investigation. It tells you that something large disturbed the carbon cycle. But the PETM already proves that nature can do this, because it happened 56 million years ago. Stronger evidence would have to sit beside the carbon signal. A volcanic pulse or a release of methane would need to be unable to produce it. The natural pulse sets the minimum work any industrial interpretation has to do. Think of a fingerprint at a crime scene. On its own, the print gives investigators a reason to ask questions. Add DNA, independent witnesses, and a reason for the person to have been in the room, and the case changes. Each piece needs checking, but their agreement is harder to dismiss. A strong technogenic layer would need that kind of agreement. Beside the carbon shift, researchers would look for specific chemical signs. Nitrogen ratios would need to show the particular disruption left by intensive agriculture, rather than a pattern caused by volcanism or ocean turnover. Synthetic materials would need to lack any plausible natural origin. Possible examples include certain microplastics, artificial radionuclides from nuclear testing, and industrial byproducts with no geological equivalent. These are separate measurements rather than new descriptions of the carbon signal. The material associations would also count. Some substances may occur separately in nature but never appear together through any known natural process. Finding them in the same thin layer would make the natural explanations work much harder. The location of the layer would have to make sense too. It should appear at a consistent depth across the globe and begin abruptly. Separate records on different continents should show the changes at roughly the same time. A slow natural transition may enter those records at different times. If one marker begins much later, it may not belong to the same event. Then the comparison with a PETM should stop working. Researchers would need to say, in plain terms, that the PETM produces one group of signs, while the candidate layer contains something the natural event cannot explain. The PETM gives them a baseline. It does not erase the candidate signal, it shows where the difference must be. The comparison asks whether patterns separate after their overlap has been measured. There is no finished checklist for this work. Researchers do not have one threshold that closes the case. The argument has to build from independent measurements that point toward the same narrow period. A carbon isotope shift may come from one core, unusual materials may be found through a different method, and chemical ratios may be measured in another laboratory. Each proxy has its own weaknesses. Agreement across those methods is useful because a single natural explanation must then account for all of them at once. One natural process may fit one proxy and fail another. The case narrows as those explanations drop away one by one. This is why one startling anomaly remains weaker than a coordinated pattern. A single odd result raises a question. 5 results that cannot all come from the same natural cause may support an answer, though it would still be tentative. The number 5 is not a formal threshold. The point is the independence of the evidence and its agreement in time. Geologists can find anomalies. They measure them, debate them, and spend careers trying to explain them. The difficult part is gathering enough independent evidence that the natural alternatives no longer fit. That task becomes harder when the record itself has missing sections. If nature can imitate part of the signal this well, how incomplete is the continental archive we would have to read? Imagine standing below a cliff made of long horizontal bands. One layer is brown, the next is grey, and another lies above it. The sequence looks orderly, like a record pressed into stone. You may assume the whole history is there if someone knows how to read it. Only the surviving parts are there. Between those visible layers, time can be missing. There may have been a period when no sediment formed. Material may have formed and then eroded before another layer covered it. Geologists call such a gap an unconformity. It does not appear as an empty space in the cliff. The missing interval is simply absent, and you may never notice unless you know which signs to check. The rock above and below the gap can touch even though a long interval is missing between them. That is how much of the continental record survives. It is closer to a damaged book than a complete archive. The same forces that build land can also erase its history. Uplift raises old rock toward the surface, where rain, ice, and wind wear it down grain by grain. Deep burial brings heat and pressure. Rock bends, and its original chemistry may change through metamorphism. A chemical signal that once existed can disappear in that process. The rock may remain, while the chemistry that made the layer distinctive is gone. Some gaps form more quietly. A shoreline moves away, a basin dries out, or sediment simply stops falling in that place. Geologists call this non-deposition. Nothing new is deposited, so that interval leaves no layer at all. Unlike erosion, it does not remove an older layer. The missing period never became sediment in that location. Later sediment may rest directly on a surface much older than itself. Put these processes together, and the record becomes a collection of pages in different conditions. Some remain readable, others are torn, soaked, or missing. You do not know in advance which part of the story was lost. The damage is uneven, though. Certain basins preserve rock remarkably well. Deep depressions that remained tectonically quiet could gather sediment steadily and keep it in place. The Karpval Craton in southern Africa and the Pilbara in Western Australia contain ancient rock that has stayed largely undisturbed. Geologists have found 3-billion-year-old microfossils there, along with chemical signals that held their form across deep time. Their preservation does not show that surrounding regions kept the same interval. These places show that old evidence can survive. They also show how selective that survival is. A good basin gives you a window, not a view of everything that happened across the planet. It records material that reached that basin while sediment was forming there. Events elsewhere may leave no trace in the same rock. Researchers have to work with the places that favored preservation during periods when something could be deposited. One window can be clear and still cover only a narrow region. So the continents may still contain an answer. A layer of shale kilometers below an undisturbed basin could hold it. But the original record has been eroded, buried, changed, or left unwritten in many places. Searching continental rock is the start of the problem, not a simple solution. A drill placed somewhere else could miss that layer entirely. If so many intervals are missing, what can the absence of obvious evidence tell us? Less than you may expect, though the limit works in both directions. It is tempting to treat silence in the rock as a final answer. We have not found a fossil city, a buried reactor, or a clear layer of refined metals. From that, you might conclude that nothing industrial could have existed before us. The reasoning feels ordinary. Large events leave marks, and no mark means no event. Gavin Schmidt and Adam Frank examined what would remain after 50 million years. They were not imagining a civilization at its height. Their example had ended completely, then passed through geological change for longer than the dinosaurs had been gone. Their expected evidence was slight, perhaps a thin carbon isotope anomaly, or a small rise in certain metals. The material could be measurable without being recognizable. Its existence in a core would not automatically tell the person holding it what caused it. A signal like that could already sit in a drawer marked as unusual, with its origin unclear. It might remain there for decades because nobody thought to ask an industrial question of it. Recognition depends partly on which question someone brings to the sample. Return to the damaged book. If someone tears out a page, the gap cannot tell you what was written there. It cannot reveal whether the sentence was long, short, important, or dull. Missing paper carries none of those details. It also cannot tell you whether the missing sentence described something real or invented. Missing intervals in sediment work the same way. The lack of a clear industrial signal does not prove that no signal ever formed. It may have formed and later dissolved into ocean chemistry. It may still exist inside kilometers of rock that no drill has reached. We cannot use a missing interval to reconstruct the signal that might once have occupied it. A page that is missing is different from a page that was left blank. This limit does not make every possibility equally plausible. A poor archive weakens an argument based only on silence, but the standard for positive evidence stays in place. The loss of one interval cannot turn a nearby anomaly into proof. Any surviving pattern still needs to beat the natural explanations. Because an ancient industrial civilization would be an unusual claim, the evidence has to be stronger, not weaker. Missing rock changes what silence can tell us. It does not change what a positive identification requires. Losing rock reduces the available evidence while leaving every surviving marker subject to the same test. That leaves both easy positions in trouble. The claim that nothing happened because we would already know is too confident. The opposite claim, that missing evidence leaves every possibility open, also goes too far. Geological processes may have erased a signal. Researchers would still need convincing evidence from what remains. What would have to survive before geologists accepted an industrial reading? Imagine one person reports seeing something unusual. You would listen, But you would also consider a faulty memory, confusing light, or an ordinary event seen from an unfamiliar angle. One witness gives you a place to begin. Now imagine 12 witnesses in 12 different countries. They do not know one another, yet each describes the same sequence in the same order and at the same time. Agreement like that changes the question. You begin asking what happened, rather than whether anything happened at all. Because they are separated, one shared source of confusion becomes less likely. Ancient sediment is judged in a similar way. One strange deposit in one basin may come from a local flood, landslide, or isolated impact. The layer can be real and unusual while still belonging to a local event. Several separated basins are different. If each contains the same kind of deposit, dated to the same narrow interval, their agreement is harder to dismiss. The basins need to be independent. Connected sites could share contamination, a preservation quirk, or one local accident. Then the repeated signal may have only one local source. Basins thousands of miles apart cannot share those local causes in the same way. Their agreement has to be explained across distance as well as through chemistry. A shared date is as important as matching chemistry. An incomplete archive makes this agreement more important. If only a few windows survive from a period, a signal found in all of them carries more weight than one found in a single core. The bar does not fall because evidence is rare. Each isolated fragment is weaker on its own. The case grows stronger when those rare fragments agree. If one surviving window lacks the signal, researchers have to explain that absence too. A local anomaly remains limited evidence. One impressive layer at one well-studied site cannot carry the whole claim. It may be genuinely hard to explain, but something unexplained today is not necessarily beyond explanation. Surprise is not the test. Researchers would look for agreement across distance, separate basins, and investigators who did not coordinate their results. The record would need to repeat the same timing and pattern in places that could not have shared a local cause. In effect, the archive has to speak through more than one surviving window before the interpretation can carry much weight. One laboratory error cannot easily explain a result repeated by separate teams. That standard changes how two familiar examples should be read, the Younger Dryas and Göbekli Tepe. Both are real and deserve careful study. Each can be examined as evidence, while remembering that one remarkable site begins a question rather than answering it. If the archive is so patchy, why do people keep reaching for the Younger Dryas and Göbekli Tepe? The Younger Dryas begins with an event we know happened. Around 12,000 years ago, temperatures fell quickly. Ice advanced again across the northern hemisphere, while megafauna began disappearing on 2 continents. The colder period lasted about 1,000 years, then it ended almost as quickly as it began. Ice cores, lake sediment, and pollen records from dozens of places around the world all preserve this change. Scientists do not dispute the Younger Dryas itself. The argument is about what caused it, because those records come from separate archives. The event cannot be dismissed as a quirk in one local dataset. For roughly 15 years, one group of researchers has argued for an impact. Their proposal involves a fragmented comet or a group of smaller objects striking Earth and leaving a thin, dark layer across 3 continents. They reported microscopic diamonds, glass spherules, and carbon markers that they interpret as signs of an extraterrestrial impact. Other researchers searched for the same material and found much less than the hypothesis would require. The work has produced publishable evidence, but no settled verdict. The impact debate is still open. The dispute concerns how well the impact markers repeat, while the climate event itself remains established. The trouble begins only when that debate is asked to support a different claim. Imagine a road lined with confident signs. One points toward a comet strike, the next points toward climate disaster, and another toward a civilization swept away. Each sign seems to follow from the one before it. But if you keep going, the road never reconnects with the evidence we were following. Even complete proof of the impact hypothesis would leave a gap. Suppose researchers verified the strike, confirmed the date, and mapped the damage. we would know that something violent happened 12,000 years ago. We would still have no evidence that people were smelting metal before it happened. Confirming a cause for the younger Dryas would answer a climate question, not a question about earlier technology. A catastrophe and a lost civilization are separate claims. A comet can destroy a civilization only if the civilization existed first, and that part needs evidence of its own. The impact cannot provide it. This is easy to miss because each step feels small. An impact makes a vanished population seem possible. Then a vanished population makes a lost library seem possible. By the time the sequence reaches an advanced civilization, the first piece of evidence has been asked to carry claims it never tested. The earlier society would need its own dates, material remains, and environmental traces. That is why the younger Dryas belongs in this discussion. It shows how separate ideas can become bundled together. A proposed impact becomes a catastrophe. The catastrophe becomes a reset, and the reset is treated as proof that somebody was erased. The steps sound connected, but none establishes the next one. A plausible sequence does not show that every link occurred. You can follow the younger Dryas impact debate with genuine interest. The science is unfinished. It still does not provide evidence for an industrial civilization. Keeping the claims separate lets impact research stand or fall on impact evidence. If catastrophe cannot carry that claim, why does Göbekli Tepe persuade so many people? Göbekli Tepe deserves to be understood on its own terms. The aim is not to dismiss the site or the people who built it. It stands on a hilltop in the Taurus foothills of southern Turkey. The site contains rings of stone pillars carved with foxes, cranes, aurochs, and abstract forms that are still not fully understood. Some pillars are more than 5 meters tall and weigh as much as 10 tons, yet their builders had no metal tools and left no written record that we have found. The oldest layers date to around 11,000 years ago and may be older. In 2020, archaeologists Gerald Hackley and Avi Gopher published research on the layout. They found consistent geometric planning in at least some of the enclosures. The stones were not placed roughly as the work went along. The builders followed a deliberate design, organized labor, and returned over generations to add more. Geometry shows a large, sustained building effort without identifying metalworking or an industrial energy system. Trouble begins when modern industry is added to it. You see the scale of the pillars and hear their age. Planning, labor, and coordination are all visible in the stone. It can be tempting to add another step. If people could build this, perhaps they could smelt metal, burn fuel on a large scale, and change the chemistry of the atmosphere. The site then becomes one surviving piece of a much larger imagined world. A carved stone enclosure is not evidence of a power grid. Metallurgy leaves slag, charcoal deposits, and changes in soil chemistry. It also leaves residues spread through layers of earth. Large-scale burning leaves ash and altered isotope ratios. An industrial system large enough to appear in ice cores or ocean sediment produces waste. Those traces belong to a different category of evidence from carved stone. We can see these effects from our own industry. Ice cores drilled in Greenland and Antarctica contain carbon, lead, and sulfur that appear when the history of modern emissions says they should. If an earlier society had changed the planet on a comparable scale, its corresponding mark would need to be present. Göbekli Tepe has the stonework. It does not have the sediment signal required by the industrial claim. The site tells us something substantial without that added story. People sustained collective work on a scale that researchers did not expect so early. They planned large enclosures, moved heavy stone, and continued building over generations. That expands what we thought early human groups could do together. Without a corresponding sediment signature, the stonework cannot support a planetary industrial claim. Calling the site industrial does not make the achievement larger. It pulls attention away from the evidence the builders really left. Once we separate the impact debate from the lost civilization claim and monumental building from industry, the original question becomes clearer. What evidence would a convincing answer require? Most of us want one piece of evidence that settles everything, an object with no ordinary explanation, a layer that geology could never make. Find that, and the question seems finished. Geologists rarely get an answer that clean. Think about a jury listening to several witnesses. One confident account may sound convincing, but it can still be mistaken. Then independent witnesses describe the same event from different places. They had no chance to coordinate their stories. Each account remains limited, yet their agreement needs an explanation. One witness cannot make the others report the same details from separate positions. An industrial signal in ancient rock would work in much the same way. Researchers would expect several independent lines of evidence inside the same narrow interval. No single result would carry the claim. The group would need one underlying event that explains why all the signals arrived together. They can be modest alone, provided their dates and physical causes line up. Atmospheric chemistry could provide one line. Ice cores or sediment may preserve isotope ratios that depart sharply from the ordinary pace of natural change. An abrupt carbon shift might look different from a volcanic episode or slow ocean cycling. By itself, however, unusual chemistry still has natural explanations. Sediment debris could add another line. Researchers might find synthetic compounds or microstructures that ordinary geological processes do not form. Technogenic materials, meaning substances usually produced by industry, could add a third kind of evidence. Then the timing has to agree. The markers need to enter the record in the same narrow window, rather than being scattered through 10,000 years of background sediment. Gavin Schmidt and Adam Frank worked through this problem in 2018. They asked what an earlier industrial civilization might leave and whether geologists could recognize it. Their paper was not a claim that such evidence had been found. It outlined the minimum kinds of conditions that a serious case might need to meet. They were defining the test before anyone tried to claim a result. No agreed checklist exists. Geologists have not settled exactly how many independent signals would be enough, how narrow the interval must be, or how unusual the chemistry would have to become. There is no accepted point system where a certain number of markers closes the case. The strength would depend on how independent the measurements are, how well their dates agree, and whether one natural event can account for all of them. Claims of certainty in either direction run ahead of that discussion. One object with a clear answer would feel satisfying. Rock is more likely to offer several moderate signals that become useful when they appear together. Their coordination is the evidence. What kind of agreement would those signals need? Imagine walking into a room where one clock reads midnight. The clock may have stopped, it may have drifted, or somebody may have set it wrong years earlier. Now walk through the whole house and find every clock reading midnight at the same moment. The kitchen clock agrees with the bedroom clock and the neglected one beside the back door. That changes what you need to explain. A shared event becomes simpler than several clocks failing independently at the same instant. One strange carbon layer in a single rock formation is like the first clock. Geologists find local oddities often. A basin may develop unusual chemistry. Burial conditions may alter one deposit, or a fault may redirect drainage for a few thousand years. Any of those could produce an isolated result. A planetary case would need records from different continents. The same signal should occupy the same stratigraphic position with the proper sediment around it. Several basins separated by oceans would have to strike the same hour. Large numbers can make a local signal seem global. Suppose one section contains a carbon excursion 3 times larger than its background level. The number catches your attention, and it is easy to imagine a worldwide event. Yet one section in one region remains local. Its size tells you how strongly that particular section changed. It says nothing by itself about a basin on another continent. The layer may be useful geology for another question, but a planetary claim requires the same timing and pattern somewhere far away. Distance reduces the chance that one local preservation quirk produced every copy of the signal. Timing is equally strict. A marker must appear in the right position relative to the rock around it. It has to fall before the correct boundary or inside the correct deposit, with the expected relationship to other changes in that layer. A signal in the wrong position does not strengthen the bundle. It creates a separate problem to explain. This standard is demanding, but it turns the issue into something testable. Do independent records from distant places point to the same thin interval? Researchers can compare timing, chemistry, and sedimentary setting instead of arguing only about the size of one anomaly. A mismatch does not vanish because the original signal looked impressive. It tells them that the records may not describe the same event. A missing match in one well-preserved basin is evidence too. Much of the work lies in correlation. A signal found in one basin has to be sought in another at the same depth, in comparable rock, and at the same point in time. Correlation also tests local preservation. If one basin concentrated a material through a burial quirk, a matching layer in a distant basin makes that local explanation harder to use for both sites. Matching depth alone is not enough if the surrounding rock records a different setting. Even if the markers line up, when should a natural explanation give way? Only when it fits the evidence less well. Imagine finding a key that opens a lock. That seems promising until your spare key opens it too. Then your neighbour's key works, along with the master key from the building office. Your first key fits, but it is no longer a unique explanation for the open door. If only one key works after the alternatives are tested, the fit carries more information. An industrial interpretation receives no credit simply for being unusual. The claim does not earn a lower standard because it would be an important discovery. If anything, the comparison has to be made with greater care. Researchers must take the strongest natural analogue and lay it against the same timing, chemistry, and sediment. Industry becomes the better explanation only when that natural comparison leaves more of the evidence unexplained. A poor natural match is useful only after the best available natural match has been tried. The comparison has to use the full marker bundle, not a simplified version of the natural event. Several natural events can imitate parts of the bundle. Volcanic activity can produce carbon spikes. A collapse in ocean circulation may leave chemical changes in sediment. Wildfires started by lightning can deposit soot in a thin, dark layer. Gavin Schmidt at NASA and Adam Frank at the University of Rochester examined examples like these in their 2018 paper. It was among the first papers to ask seriously what an ancient industrial civilization would leave behind. They did not conclude that the industrial case was strong. They found that separating the cases is harder than it first appears because geological records compress time. A century of industrial output beneath 66 million years of rock would form a layer thinner than a human hair. Some natural events leave thicker layers. At that thickness, a century and a natural event may blur at the available resolution. Ambiguity is a finding when it comes from making the comparison honestly. It means the surviving rock may not contain enough detail to separate two causes cleanly. Both explanations may fit the chemistry while differing in details that burial removed. Choosing the more interesting cause does not recover that missing information. Researchers have to state what the layer supports, what it cannot distinguish, and which additional marker would change the comparison. Stating the limit keeps the story from becoming stronger than the rock that supports it. Independent agreement can still make a signal stronger. A carbon spike in one place is weak. Find the same spike with the same nitrogen ratio at the same stratigraphic depth on another continent, in another basin, and beside a collapse in pollen, and the bundle becomes harder to explain naturally. Different teams may collect each line from different rock. One laboratory may measure carbon, while another studies pollen or nitrogen. They have no reason to coordinate their results, and their methods do not fail in the same way. If the evidence agrees anyway, a common event becomes a better explanation for the pattern. Shared depth and timing are what connect those separate measurements. The available record has to preserve the pattern across more than one place. One strange marker cannot do that alone. But suppose a marker bundle once did exist across several continents. What would millions of years of burial and alteration do to it? When you imagine something buried deep in rock, it may seem as though it is waiting there unchanged, a little like a letter inside a time capsule. The paper may fade, but you expect the same words to be readable when the capsule is opened. A time capsule isolates its contents. Buried sediment remains part of the changing rock around it. Millions of years inside rock are not that gentle. Think of a note forgotten in a coat pocket before the coat goes into the wash. After one cycle, the ink has blurred. After another, letters begin to separate. Some remain clear while others spread into the coat lining. Keep washing the coat and the note may hold only a few words and part of a line. Each wash keeps some ink while losing more of the original arrangement. You can still read something, but it is no longer exactly what was written. Every cycle has changed it. Burial does this to sediment. As sediment gathers over millions of years, the growing weight compresses the layers underneath. Water is forced out, minerals recrystallize under pressure, and new chemical compounds form where older ones had been. Geologists call this diagenesis. It is the slow chemical change that turns loose sediment into solid rock. Compaction and chemical change occur together as sediment becomes rock. Diagenesis does not happen in one clean step. The record changes as the rock forms. With deeper burial, pressure rises and heat comes from below. Rock that has already changed begins changing again. This is metamorphism. Temperature and pressure become strong enough for even stable minerals to rearrange. A faint original signal may be stretched, folded, or made unreadable. The rock may survive even after the proxy a researcher wanted has vanished. Fluids create another problem. Groundwater and hydrothermal brines move through cracks and faults over long periods. They remove some elements and deposit others. A chemical ratio that meant something when the sediment formed can drift away from its original value, blend into the surrounding rock, or disappear. The elements do not have to travel far. Movement within the same layer may still weaken the ratio that a researcher hoped to measure. So when geologists say a signal survived, they rarely mean that it remained intact. The rock may preserve an altered version of it. The chemistry and shape can differ from what first entered the sediment. Researchers must ask how much survived and what changed after deposition. Alteration can stop short of complete erasure. Some ratios remain more stable than others. Certain features inside minerals resist change. A signal that began strong enough or differed sharply enough from its surroundings may remain readable after the rock around it has been altered. The evidence underground is unlikely to be pristine. It is closer to the note from the coat pocket, something real, broken into fragments and changed by the process that preserved it. Enough may remain to read, but only if we understand what happened to it along the way. Which geological settings can still preserve enough of the signal? Imagine investigators searching for surveillance footage after a building fire. They want to know where the fire began, how it moved, which doors stood open, and which sprinklers failed. Most cameras were destroyed. A hallway camera kept 30 seconds. A stairwell camera saved another clip, and one in the parking garage kept a minute. No camera records the whole fire, and every surviving view has blind spots. The surviving clips do not give investigators a continuous replay. They offer a few short views of a much longer event. Geology works with the same kind of incomplete record. It does not preserve a clean sequence covering 4 billion years. It gives researchers scattered sections where local conditions happen to protect part of the evidence. No single section can represent the full planet or every interval. Time produces more than two possible outcomes. Evidence does not have to remain intact or vanish completely. Often it survives in part. Some basins gathered sediment quickly enough to bury organic material before oxidation destroyed it. Later tectonic movement folded some old rock upward, exposing it at the surface where geologists can read it again. Partial evidence can still support comparisons between layers before and after a change. These exposures create stratigraphic windows. They are columns of layered rock where changes in chemistry, isotope ratios, and microbial signs can be followed through a recognizable interval. That interval provides a baseline on each side of an anomaly. Some windows preserve pieces of large changes in the Earth system. They record shifts in ocean chemistry, carbon cycle excursions, and transitions that affected more than one continent. Research on Archean cratons and Proterozoic basins shows that preservation can be selective. With the right environment, burial conditions, and a type of signal, evidence can survive despite everything that later happened to the rock. Stable ratios and mineral features may persist longer than fragile chemical details. But a few surviving clips are easy to overread. Smoke in one hallway may lead an investigator to guess where the fire started. A second clip from another stairwell can force the whole explanation to change. The missing footage affects how the surviving footage is understood. Geological gaps do the same. A partial record can appear to contain a pattern, especially when we already expect to find one. The problem is more than inconvenience. Human beings are good at connecting fragments, even when the missing sections might have changed the result. Missing sections can change the pattern a reader thinks they see. That is why scarce evidence cannot lower the standard of proof. A small window is easier to interpret as support for an idea you already hold. The less complete the record, the more carefully each conclusion has to be tested. This temptation has caused trouble in the field before, so a candidate must survive both natural alternatives and the bias introduced by missing sections. Enough windows survive for serious research, though they cannot reconstruct a complete history. Some proposed traces of ancient biology will survive careful testing, while others will not. Some claims stay close to what the rock shows. Others depend on what someone hoped the missing sections might contain. After all that alteration, which traces remain realistic and which belong mostly to fantasy? Think about a room the morning after a party. The furniture is back in place and the glasses have been washed. No obvious object may remain. Yet there is a stain on the floor, a receipt on the counter, and something unusual in the air. Those smaller traces can tell you what happened after the objects have been put away. The stain records where something spilled, while the receipt records what entered the room. Neither needs the glass to survive. Geology works with the stains and the receipt. Physical objects break apart and dissolve. Chemistry and patterns of distribution may last much longer. That is why the most realistic survivors are indirect. A metal tool corrodes. Burial and pressure can change a structure until nobody could recognize it. An isotope ratio inside sediment does not need the original object to remain. The chemistry carries its own record. Indirect evidence is no easier to find. It simply has a chance to outlast the hardware. Chemical anomalies come first. Industrial processing or large-scale combustion can concentrate certain elements. Their presence is only part of the evidence. Geologists can also study how they are spread through a layer, their isotope fingerprint, and the ratio of one form to another. These ratios are measurable today in cores from lake beds and ocean floors. A layer-wide distribution tells more than one enriched grain. Stratigraphic disruption adds another line. A layer may suddenly contain different material, followed later by a recovery. Natural geology can produce such changes, so disruption alone tells us little. The result becomes harder to dismiss when the same layer also contains unusual chemistry. The recovery helps place the beginning and end of the disturbance. Synthetic particles could join the bundle. Fly ash is left by high-temperature combustion. Its shape and composition differ from natural volcanic ash, and it is used today as a marker of the industrial era in ice cores. Under suitable preservation conditions, chemically similar material from an earlier time might remain. Some isotope traces could survive as well, including selected radiological traces. Ratios may point toward enrichment or processing. Their distribution would need to fit a technological source better than any natural one. None of these signals works alone. The sedimentary basin must have gathered material continuously and escaped too much disturbance afterward. Researchers need layers from before and after the anomaly so they can compare the timing. They also need a site without the signal, which helps show that the result is not background noise. These conditions are demanding, but they are possible. The methods already exist, and so does the rock. We do not yet know whether the signal exists inside it. The uncertainty is whether an ancient signal survived. Indirect evidence often feels weaker because the object is missing, but effects can outlast their causes. A footprint remains after the foot has gone. A chemical layer can sit for millions of years after everything that once stood above it has been recycled. Indirect describes the form of the evidence, not its strength. One faint anomaly may be weak, while several matching traces can support each other. The record survived in another form. A footprint is useful only when its shape and context distinguish it from other marks. So maybe we would know has a limited meaning. It does not promise a ruin or an intact artifact. It means a bundle of chemistry, stratigraphy, residues, particles, and carefully chosen isotope traces that agree inside the same layer. If those are the realistic survivors, which expectations belong mostly to fantasy? Most of us imagine a shelf of relics. There may be a skyline preserved in stone, like ruins only a few thousand years old. Perhaps a power grid remains in a recognizable pattern. We may hope for one carbon spike that can only mean industry. At the back of the shelf sits the ideal discovery, a small designed object, clearly artificial, inside a layer older than anything humans are known to have made. The designed object is appealing because it seems to remove the interpretation step. One clear view of that object would seem to answer the question. Deep time makes most of this unlikely. It does not preserve landmarks the way recent history sometimes does. Imagine a ship sinking in the ocean. At first, you might find the hull, the masts, and the name painted on the side. A recent wreck in calm water may keep these features. Across geological time, the ocean keeps something else. The ship disappears, while rust changes the sediment where the metal rested. The shape and the name are gone. A chemical trace remains. Rust can spread beyond the hull's outline, leaving chemistry without the ship's shape. 1 billion years is not the same as leaving an old ship in slightly deeper water. That interval can flatten mountain ranges, recycle ocean crust, and reduce complex structures to their original chemistry. The broad verdict from this work is direct. The most visually obvious evidence fails first. Skylines are buried, eroded, or carried back into the mantle. Power infrastructure corrodes over centuries rather than millions of years. Even an isolated industrial carbon spike may be mixed, diluted, and covered by natural variation. The gap between centuries and millions makes infrastructure an early loss. Large diffuse effects can last longer. Atmospheric ratios may shift over millions of years. Isotope columns can retain evidence of planetary chemistry, describing the planet left behind rather than the civilization itself. Diffuse effects can appear in more than one archive at once. Removing the imagined relics does not empty the search. It leaves a harder kind of evidence to interpret. This is not a retreat from the original question. It matches the search to the material that deep time can preserve. A discovery no longer has to resemble a familiar object. It has to form a readable pattern in the correct layer, with independent measurements pointing toward the same cause. The search asks what an object changed in its surroundings while it existed. In practice, the conclusion would come from chemistry and careful inference. It would probably be expressed as a degree of confidence rather than certainty from one object. Confidence rises as independent lines agree and natural explanations fail. So when we answer the question, what kind of knowledge would we really have? The answer cannot be reduced to yes or no. If an industrial civilization collapsed here 100 million years before ours, ruins would probably not tell us. Its buildings and roads would be gone. Metal, glass, concrete, or any equivalent materials would pass through the ordinary machinery of geology. They could be eroded, subducted, crushed, or recrystallized beneath kilometers of younger rock. Erosion removes shape, subduction removes the surface, and recrystallization can change the chemistry. Question 12 in this line of research puts the point plainly. A civilization's longest-lasting signature is unlikely to be its structures. Structures do not survive for that long. Chemistry has a better chance. Industrial combustion can shift isotope ratios. Manufacturing may leave synthetic compounds that do not form without it. Pollen profiles can be interrupted and rearranged. Soil may retain the particular effects of large-scale agriculture rather than the slow change of natural succession. Gavin Schmidt and Adam Frank laid out this research question in 2018 and argued that it deserved serious scientific effort. They described a bundle of evidence because no marker can settle the case alone: geochemical, stratigraphic, and synthetic signals would have to agree in the correct depositional setting. Their agreement would be harder to explain naturally than any one result. The measurements also need enough independence that they do not all fail in the same way. That is the kind of knowledge deep time may allow. It would not be a ruin or a museum artifact. The evidence would be chemistry in a particular rock layer, supported by several independent measurements. The boundary is clear. No such bundle has been found. We have not identified an older layer with that profile. This is a statement about the evidence available now. It is different from proving that no such layer ever formed, and it is also different from treating every unexplained layer as a candidate. No candidate layer has crossed that threshold. The Anthropocene gives us one known example, our own. It has not entered the deep record because we are still depositing it. We are too close to examine it as a geologist 100 million years from now might. For earlier periods, the search remains open. That describes the state of the work, not permission to choose whichever answer feels appealing. The evidence says that we have not found an earlier industrial layer. It does not show that none ever existed. We can watch our layer form, but we cannot test it after deep alteration yet. Two extreme answers both miss what geology does. Evidence does not have to remain unmistakable or vanish completely. Deep time makes the record difficult to read. It can leave evidence at the wrong resolution, altered enough that the right question has not yet made it legible. Between intact and vanished lies evidence that survived in altered form. So the answer is bounded by chemistry and stratigraphy. It also remains bounded by the lack of a confirmed signal. What we have is a method and a search that has barely begun, rather than an object that settles the matter. That is enough to say what the evidence currently supports. The method identifies what to compare and which natural causes must be tested against it. What would make one strange layer a techno-signature? The scientific work begins there, and no settled list exists yet. You might assume that finding the layer is the hardest part. Researchers must drill to the right depth, recover usable material, and date an anomaly accurately. That work has taken careful effort across decades. But a second problem remains after an unusual layer has been found. Someone must determine which causes could have produced it. A clean date lets researchers place separate markers inside the same interval. That is the live frontier. It is a problem of evidence. The issue is not simply whether something happened. Researchers need criteria for calling a signal intelligent after heat, pressure, and biology have altered the layer for 66 million years. Imagine a future geologist examining our century. She has the layer and can measure carbon isotopes, heavy metals, and microplastics in its sediment. Those measurements do not reveal intention. No instrument can read the purpose behind the particles. She has to reason backward from effects to a cause, compare natural processes that could mimic each part, and account for everything that changed the archive. She can infer a cause only by comparing patterns, not by reading motive from the material. An older layer has passed through more of those processes. Each one makes the original signal harder to reconstruct. Hearing something faint is only part of the problem. A whisper and wind both move air, but they do not have the same structure. The pattern and specificity differ. Researchers need to decide what structure would remain recognizable after 60 million years of overprinting. That is a question of definition, and it has to be answered with criteria. Specificity means finding an arrangement that known natural processes struggle to reproduce. Ambiguity cannot be used to place a preferred story inside a gap. Uncertainty is a reason to define the evidence more carefully. The test must separate a signal from natural noise that only resembles one. This takes time, but a weaker definition would not hold. Uncertainty narrows the claim to what the surviving marker can support. Researchers working on technosignature detection are building frameworks for this problem now. They are asking what geological signs an intelligent invention could leave that natural processes could not, after enough time had passed to erase almost everything else. No framework has yet produced the settled list the question would need. Rigor at this edge of the work means specifying what a candidate must show before it earns the name. Excitement about what may have happened cannot replace that test. The original curiosity still belongs here. What changes is the footing beneath it. A real layer may contain a real anomaly, while the cause remains unsettled. The researchers reading it have spent careers learning how rock and time alter evidence. Their work moves the question from mood toward method. That experience helps them recognize alteration before they interpret the anomaly. When Earth leaves one strange layer, what would count as a real technosignature? The Silurian Hypothesis asked a narrower question than its name may suggest. It did not ask whether an earlier industrial civilization existed. It asked whether we could tell if one had. The search itself depends on keeping those two questions separate. After 50 million years, the most familiar evidence would probably be the least useful. Buildings disappear, metals corrode, thin out, and enter the surrounding sediment. Roads and towers lose their recognizable shapes. Satellites do not remain as satellites. Even plastics, which can persist for a long time in geological terms, have limits. Once those outlines are lost, the remaining material may be impossible to read as intention. Chemistry may last longer than those objects. A thin band of sediment can hold a change in carbon, an unusual isotope ratio, or a temperature rise that appears beside a chemical boundary. These signs can survive because the planet's response was deposited with the sediment. The original source may be gone while part of its effect remains. A geologist would compare that band with ordinary layers immediately above and below it. One sign would not be enough. Carbon excursions have natural causes. Temperatures can rise without industry, and isotope ratios change for more than one reason. A geological technosignature would need several anomalies inside the same narrow interval, with each one supporting the others. The pattern would also need to fit an industrial cause better than the natural alternatives. The timing must be tight enough to connect the markers to the same event. At present, no such bundle has been found. The search has not crossed that threshold yet. Its absence does not prove that one never formed. Earth's geological archive is incomplete. Some old rock no longer exists. Other layers have been folded, heated, or carried beneath the crust until their original chemistry became difficult or impossible to read. Silence in that kind of record cannot settle the question by itself. The archive became incomplete through selective preservation, not through deliberate destruction of records. It also cannot be used as proof that a civilization was there. Any candidate layer would still need markers that survived, agreed in time, and resisted the strongest natural explanation. That agreement must hold across more than one depositional setting. Gavin Schmidt and Adam Frank put this problem into words in 2018. Their question is still open because the criteria are not finished. Researchers are still working out which markers could last for tens of millions of years and remain specific enough to identify technological activity. So the trace, if it exists, would not be the city. It would be the faint chemical effect the city left around it. It records what a system did around itself, not who built it or why. A layer like that may remain somewhere in the rock, or there may be none to find. The chemistry can preserve a signal, but it cannot tell us more than it contains.